Welcome back to Cypress Academy PSoC 6 101. In the last video, I showed you how to use a PWM to control the brightness of an LED. In this video, let's put the PWM to work controlling my robot's servo motors. We'll add the PWM functions to our BLE Controlled Main Robotic Arm project, which we called Main Controller. The servo motor in my robotic arm requires a train of pulses with a frequency of 50 Hz, which is also known as a period of 20 milliseconds. And the pulse width needs to be between 1 and 2 milliseconds. At 1 millisecond, the servo motors are turned all the way to the left, and at 2 milliseconds, they're turned all the way to the right. At 1.5 milliseconds, it's right in the middle. So, to make the math work, we'll choose a 4 megahertz clock and pre-divide it by 4, which means that each of the PWM clock ticks will be 1 microsecond. Then we'll set the period to 20,000 so we can go from 0 to 20,000 microseconds, which is also known as 20 milliseconds. For a 1 millisecond wide pulse, also known as 1,000 microseconds, I'll need a compare value of 1,000. This also means that 1% will be 10 PWM clock ticks. Now I can set the compare value with software between 1,000 and 2,000 to give us full range of control over the motors. I'll start by dragging and dropping one PWM from the catalog onto the schematic. Let's set up the period and compare to 20,000 and 1,000 respectively. Turn on the divide by 4 pre-divider and click OK. We want to control 2 motors, so let's copy that component and paste a second one into our design. It will be named PWM_2, and that's convenient since PWM_1 will control motor 1 and PWM_2 will control motor 2. The copy-paste function is also nice in that all of the settings from PWM_1 were copied over to the PWM_2, saving us some time. Now, let's add 2 digital output pins to our design. I like the copy-paste function, so I'll pull in one and rename it to M_1 for motor 1. A quick copy-paste, and I now have M_2 as well. Let's connect those pins to the PWM output line on the components. Next, we'll need a clock. I'll drag and drop a clock in and set it to be 4 megahertz. Then wire it to both of the PWMs. One of the most forgotten steps in using a PSoC Creator design is to assign the pins. So let's do that now before we forget. Go to the pin settings and we'll set M1 to be P02 and M2 to be P55, which will match up to the pins on the Arduino Shield I'm using. Let's generate the application and start working on some firmware. Create and edit the file pwmtask.h. Remember, I said we're going to put all of these things into separate files so each of the tasks makes sense by themselves. Add the #pragma once and the includes for FreeRTOS and the semaphores. Next, I will create 2 enumerated types, one for the motors called motors_t and one for position called motor_pos_t. These enums will be used in the structure called PWM_message_t that the other tasks will use to communicate with our main PWM controller. All right, let's define the structure to send messages to the PWM. This structure will allow me to tell the PWM task that we'll create here in a minute what motor we want to change, whether we want a relative or an absolute change, and a percent change that we want to make. I'll call this structure PWM_message_t. Finally, I will define the function prototypes for the motor task and a helper function called getMotorPercent that the other tasks can use to find out the current state. In other words, the current position of the motors. After the PWM task.h header file is built, we can go ahead and update the main_cm4.c file. 4 things need to happen. First, I need to add an include for the PWM task.h. I need to create a variable for the PWM queue. I need to initialize the PWM queue, and I need to start the PWM task. When you have different tasks communicating with each other via an RTOS queue, there's always the question about where you define and initialize the queue. I like the main function to own these global-ish variables, and then I'd like to tell the other files about them in a file called global.h. So create global.h, add the pragma once, put in includes for free RTOS and semaphores, define the xturn for the PWM queue. Now the other files can get access to the queue just by including global.h. Now create and edit the PWM task. The only purpose of the PWM task is to take a message from the other tasks in the form of a percent, meaning a number between 0 and 100, and then turn the percent into a pulse width between 1 millisecond and 2 milliseconds. And finally, turn the pulse width into a compare value, which can be written into the correct PWM compare value register so that you get an output pulse of the correct frequency and width. I'm going to want 3 pairs of functions: percent to pulse width and pulse width to percent, PWM compare value to pulse width and pulse width to PWM compare value, and finally, percent to compare value and compare value to percent. So, how do I do that? Well, the math is simple. Look at this graph. On the x-axis, I have a pulse width in microseconds, and on the y-axis, I have a percent. When you have a pulse width of 1,000 microseconds, you should have a percent of 0. Here's the first point on the line. Then, when you have a pulse width of 2,000 microseconds, you will have 100%. That's the next point on the line. From Algebra 1, we remember y equals mx plus b. So the formula that turns pulse widths into percents is percent equals slope times the pulse width minus 100%. The slope of the line is rise over run, or 100% minus 0% over 2,000 microseconds minus 1,000 microseconds. And that can be arranged into percent into pulse width like this. Pulse width equals percent plus 100 times the slope, which is 2,000 microseconds minus 1,000 microseconds divided by 100 minus 0. Or simplifying further, pulse width equals percent times 10 plus 1,000 microseconds. So let's start this thing by creating the helper functions. First, define the ranges of our pulses, min microseconds and max microseconds. Then define the PWM parameters, PWM clock and PWM divider. These could be read from the schematic, but I wanted to make this simpler to understand, so I'm hard coding them here. Next, derive the number of PWM ticks per microsecond. Now I can build the helper functions. Percent to pulse just takes a percent and turns it into a pulse width with the formula I derived earlier. Then pulse to percent does the inverse of that. The 2 helper functions to turn compare values into pulse widths and pulse widths into compare values. These 2 functions use the settings on our schematic to figure this out. And finally, 2 functions to turn compare values into percent and percent into compare values. Now, in my program, I can use these helper functions to set the PWMs using percent, or find out what percent is currently set by reading the compare values of the PWMs. The next function I will build will be used by other tasks to look at the current state of the PWMs in percent. I'll call this function getMotorPercent. The getMotorPercent function takes as its input either M1 or M2. Then it looks at the PWMs and figures out what compare value is being used by that PWM right now. Then it uses the helper function compare to percent and returns the current percent value of that motor. Now I'll create the PWM task. When the task starts, I'll start the two PWMs using the start API. Then in the infinite loop, I'll wait to receive an RTOS command from the PWM queue. When I get a command from the queue, I'll figure out what the hardware and counter numbers are so I can use the appropriate macros. Then what I'll do is if the message coming in wants to make a relative change in percent, I'll get the current compare value, convert it to percent, and make the change. If the message calls for an absolute change, I'll make the change directly. Then I'll update the compare value of the appropriate PWM. That's it for the PWM task. Now I need a way to test this, so I'm going to add it to the UART command set that we defined in an earlier video. In uart_task.c, I need to add includes for global.h and PWM_task.h. And down in the UART task, I'm going to use the commands O and P to change the relative percent value by -10 and +10 respectively. And I'll use the commands K and L to do the same thing for motor 2. In the case statement for the command P, I'll set the message to control motor 1, I'll set an absolute percent, and then I'll set the percent change to -10. Then cue the message and break. Now I'll do the same thing for the other commands. In order to make the debugging easier, I'm going to add a command to print out the current status of the motors. So add the case statement for the S that printfs the get motor percent for M1 and M2. Are we done? No! We can't forget to add the messages to the help command. And that's it. That's the beauty of an RTOS, simplifying complex designs. Let's build, program, and test. Now we have a functioning UART controlled robotic arm, but we're not done yet. This is supposed to be a BLE controlled robotic arm, so we still have a little more work to go. In the next video, I will walk you through setting up an I2C control interface. You can post your comments and questions in our PSoC 6 community, or as always, you're welcome to email me at alan_hawse@cypress.com or tweet me at AskIoTExpert. Thank you.